Hey guys, welcome to yet another graduate seminar. We have a speaker, Logan Nott, speaking about combinatorial game design. It's going to be a two-part, very exciting stuff. Sure. What do you do?
First off, for those of you I haven't talked to, how many of you heard of combinatorial games?
Well, you mentioned it to me before.
Yeah. Okay, so game theory, put it as precisely as possible, is the study of sequential two-player games of perfect position. So what that means is you have two players, they alternate turns. There's no random chance. Both players know all the moves are available to them at any time. They can see what their opponents do. And that's basically the thing we're working for the paradigm. So Hackenbush specifically is a game for two players. It's called Red and Blue.
Oh, yeah, blue and green.
I'm working. The book I'm using calls them red and green, and I get
Blue plus epsilon for some value of epsilon spread.
It's just in the corner, just right, red is actually more big. We're going through it.
exactly. Okay, so we have a player, blue and green, and we have our board, which consists of the ground, and then a bunch of branches drawn connecting to the ground in some, well, basically any possible orientation you want. Basically, we're making a multi-track. Want to be super technical. This is a valid package.
Okay, and you use, the starting position is empty there, and you add branches each turn?
No, you start with a bunch of branches on a board. This is the starting position. And a move in the game is our player blue erases one of the branches of their color. Any branch that is then not connected by any path to the ground is also.
So sort of like it falls by gravity, kind of.
Exactly. So green, and let's say they erase this branch. Well, we would make it, they go here, and then that branch falls along the path.
Wait, so blue and green can erase any color?
Only their own color. So they can erase any branch they want.
Okay.
So that was an advanced position. We're going to start small. The most simple position that's not actually trivial is the position with a single branch. So if blue goes first, yeah, if green goes first, he loses immediately because he can't make any moves. Which I should have mentioned this before. How you win this game is you're the last person to make a legal move, or alternatively, you lose the game if there are no legal moves for you to make. So now that we have, well, a blue branch, same thing happens if you have a single green branch.
So sorry, I missed it. Why is green removing this green branch an illegal move? Why
Oh,
is
that green branch is there, it's supposed to be erased. There's stuff, there's
Oh.
stuff left over.
Oh.
That's not-
Oh.
That is the artifact green game artifact.
oh, so there was no.
You are correct. If there was a green branch, there would be a legal move for green.
Okay.
Which means we're going to add a green branch. In this position, whoever goes first obviously erases their own branch. Whoever goes second erases their branch, and then the first player loses because they have no more legal moves. So there's a reason for the second player. I'm going to write that in.
Previous position favored a particular color, this one favors a particular order.
Exactly. This position is not biased towards either player, which is an important concept of combinatorial game theory. Some positions are biased towards one player, some positions are not. This is an example of one that is not biased towards. we can bias it back towards another player by adding another branch. Say, if I do that, well, now clearly blue is the only one that can win this game. Because if they go first, they cut one of their branches, green cuts theirs, blue's the last one to be remaining, and vice versa. So now we have the concept of a balanced game. And we have bias. I guess we're thinking a bit.
And just for completeness, the balance is when it's not biased towards either blue or green and biased stuff.
Right. Balance specifically means the game is the second player. Alternatively, first player. So I'm going to leave that there. So now that we know what happens in that position, let's start stacking branches on top.
So wait, sorry, Logan, is there a starting position such that it's completely fair for both players?
In terms of either player being chance to win?
Yeah,
or-
like equal chance of winning.
Well, this position, for instance.
Well, this one favors the first player, right?
But the first player is taking branch.
Oh, it's picked at random?
Well, for the analysis purposes, we're assuming, we run the analysis assuming either player goes. How we actually analyze this position is we look at every single move each player can make, assuming they go first. And then,
Because if you don't randomize it, then for a finite number of branches, there you can't have both people. Can't be unbiased. It's a finite number of branches, then at some point, we won first.
so basically all analyses are conducted, assuming we look at blue going first, then we look at green going first. And then once that full analysis is done, we conclude it in bias. The game trees can get a bit annoying. So now, as we stack branches on top of each other. I love this. If we do that,
No, but
exactly, it's clear that blue is the only one that can win this position. Because, well, if they go first, they cut everything.
I was just saying, he's got a game-winning move if he goes first, but if the other guy goes first, we're basically back.
Yes. So what happens if we give the other guy another move? Say, here. That's a show hardening. So if we do this, well, now green is forced to. If green goes first, they chop this branch, bringing us to a balanced position where blue is forced to play. And a balanced position means who's ever forced to play is losing. If blue goes first, well, the only legal move is to cut this branch, and then green cuts it. So we sort of have a situation where this dual branch is good, but not as good as a single green branch. So now we're gonna add another copy of this. So we have a second copy. So now if we play this game, let's see, blue goes first, they cut here, chopping this entire tree down. Green would cut here, bringing us to a balanced position with blue forced to win. Play, so blue would lose. And if green goes first, this position should be perfectly balanced.
But, yeah, that makes sense.
Yeah.
Green would wind up back in the balance.
So we sort of have the case that two of these things exactly equal one of the green branch.
Okay.
You can already understand here. So going to write down one half of this. I'm just going to do a little bit. Basically, one half, and this branch is effectively more half. If you want to look at it like that, which is kind of where we're going. We're going to start finding numerical values to our package because they're like numbers. Numbers are useful. Keeping that idea in mind,
So then so what we're currently doing is we're finding out which Hackenbush positions, starting positions, should be equivalent for the defined means of numbers.
exactly. So clearly this position, well, let's start with something not as mind-breaking. We're going to assign to blue a single blue stock value. The value plus. Likewise, we're going to assign to green the value minus. And here's one of the main assumptions of combinatorial game theory. If we have a position that has values plus 1, added to a position of value minus 1, well, what's the logical thing?
Who's saying 0?
You add the values together to get a position of value 0. So this is important enough in its own part. A bound position is one that has a value 0 and vice versa. Any 0 position is bound. And by that I mean second player.
Okay, so now positions that differ by a balanced position. Obviously.
Yes. So if I were to say exactly that, so you can sort of, so if I had a 0 position and I had blue stock, we had down the value of 1. Because 0 plus 1 is 1. Which means, using this idea, you sort of have that blue-green stock from earlier kind of has value 1/2. You get 2 copies of it, minus 1 equals 0. And now that I'm going to actually take this thing. I hope that shows.
There's only, I only had the green one.
I don't know if it's going to be fine enough for it.
Yeah.
Run downstairs and see if there's a better green marker.
Yeah, it's kind of not showing up that well.
You can roll it. Okay. So we're going to find this value positive. And if we flip the colors, we get -1. So now you're probably thinking, okay, we have 1/2, we have 1. We can kind of get all the other integers by keep stacking the same colored branches on top of each other, either vertically or horizontally. That'll work. So can we get other fractions? Like 1/4, 1/4, third, 7, that sort of thing. Well, we can get, unfortunately, I can't prove this claim, and neither the book I found it, which is unfortunate. But it's not too hard to construct a position that has value 1/4. You add another green branch to them. And if you want to get 1/8, you can add another. You can essentially keep going like that. There's also other ways to construct it. And you can get 3/4 by stacking the blue branch on top of this, but also by taking 1/4 and subtract the 1 minus 1/4 will give you 3/4. I know I'm not writing all that because it's a bit annoying to do. But I'm going to make the following claim without proof. Any fraction in the form fraction of the form n over 2k, where n and k are integers, is a valid position in finite check. Unfortunately, the book I found and did not prove it.
Almost some induction on what you already said, right? You could make any power of 1/2 by doing this successively, then you add in together.
Yes, exactly. And you can also get other positions by, you can get 3/4 multiple ways.
Exactly, you could subtract one, or you could add a 1/4.
Exactly. So we have the geometry of finite two color package, sort of. For any position, we can assign a number. If the number is positive, blue win. If the number is negative, green win. If the number is 0, it's a win for the second player. So from that, we have, like I said, we have finite two color Hackenbush essentially solved. In any position, you can tell us you win. So
Yeah, it's just a matter of reducing it to a fundamental simple position by subtracting way down.
exactly. Or even, yeah, position we already know the value of. So now we're going to be a little bit more interesting. There we go. So, I'm looking black for this. We're going to add a third color. Because that's the obvious next step, right? That third player is just a third color, which either player can cut. Because in blue Hackenbush, there's sort of no incentive to actually make a move, because every move you make, you're moving one of your pieces from the board. But if we add a third color in, well, now the players kind of want to move because they can cut a different color that's not their own, and they're depriving it from their opponent, instead of cutting their own pieces. You're probably wondering why I had to do a single pink line.
Because this would be a balance. Well, no, this is not balanced, right? And then the second person.
This is the first player win.
Yeah.
Yeah. So if the first player wins, so obviously the value can't be 0, because we assigned 0 to a second player. The value of this position is not 0. So, well, what does it even have a value for that? If I start adding, if I take whatever this value is, minus 1/2, which is green, blue. Well, let's see. If this position, x minus 1/2, if green goes first, we're going to cut the pink line because they're the only one who can win. If blue goes first, they're not going to cut this because green's the only one who can win, so they're going to cut this blue branch. And then green is going to cut the pink branch. And then green is the only one who can win. So the value of this position, I'm going to call it x for now. Minus 1/2 is what? 0. And if I add the analysis, and 1/8, and 1/16, and 1/32, and in fact, is less than 1/2k for any value of k. And flipping the colors is the exact same argument in reverse. So whatever the value is less than all positive fractions, greater than all negative fractions, and not 0. So now we have to wonder, is this thing even a number? And our normal sense is saying, hell no. So we're going to roll with it anyway. And we're going to assign it a number.
Yeah, it's clearly not a rational. It can't be a rational. Pointing point would have to be both 0
But it also can't be real, because remember, between any two fractions,
Yeah,
you can find a real. We're going to give this position with a single pink branch a name. We're going to call it star. If we have star, we can do some pretty interesting things. So, from star, what happens if we add another column? Well, let's see. If blue goes first, they chop one of the stars. Green top the other one.
It's still additive inverse.
Yes.
Oh, God.
So, as Bryce just pointed out, it's very clear to see from this position that it is in fact balanced. So, star plus star is zero. So star is its own negative, kind of like zero, but it's not equal to zero. In combinatorial game theory parlance, we say star is confused with zero, and we write it with the concatenation symbol. You can also get other star values like 1 plus star, which is a position with a pink and blue branch, which is quite confused with 1. And you can do that for any natural number you want. You're going to have a n plus star position that's confused with n. That also holds for all the dyadic rations too. So now we have this weird additive inverse property. We have star. We have the balancing. Remember how we stacked blue and green branches on top of each other? Well, the next logical step is to start stacking pink branches on top of each other. At least in my mind it is. I don't know about you. So,
Watch the stuff in my mind.
I'm sure Conway was thinking that maybe he's coming up with this stuff. So now, we have a slight problem. This position is clearly a first player win, because the first player is going to chop the bottom right. So
Which is exactly.
exactly. So the other position is a first player win, and we know it's not zero. So we can kind of see the same thing is going to happen as before. We keep adding successive negative fractions. The same analysis holds. Meaning this thing is also squeezed in between all the dyadic rations. So what happens if we play the position x plus star? Here, well, let's see. Whoever goes first is going to chop this branch, leaving us in a zero position. So x plus star can be reduced to star plus star rather easily. So this position, if it's reducible to that proof is not zero. So this thing is not zero. Whatever x is, it's not so. The star is done with additive inverse. So x is not star, but it's still squeezed in there like star. So we're just going to give it a new name. Star 2. Not to be confused with the adding star to itself or multiplying it by 2, obviously as the notation sort of suggests. It turns out that star 2 is, I hope this is out. I forget if it's less than or greater than star. I actually it's less than star. Should be. Either way, that's just more of a thing that shows up. We can keep going. We can make star 3 and star 4 or star 5 just by adding successive pink branches on top of each other. So you can get this whole infinite sequence of new numbers. We're not going to call them numbers because that's going to get a bit confusing. We're going to call them nicknames.
I've heard you mention before.
You have something, you take coins that have a pile, you take turns of moving coins from a pile. The last person who can't move a coin is loses. If you play NIM with a single coin pile, it turns out the value of that position is exactly star n, where n is the number of coins. Hence, NIMBER. Because this analysis exactly works for NIM. So this thing is a NIMBER. And we have a lot of them. We have an infinite number of them. all of which are squeezed in between all of the fractions. Right, start erasing it. And if you're into.
I think Phil has a question.
Well, we can get one for every single natural number at bare minimum, so it's a countable number. I don't know.
So that's true for any infinity. If any infinity is at least countable.
I don't know of a position
The
with a value of
infinity is
star.
yeah.
I don't think you can construct.
That'll still be countable.
Yes, it can still be countable. So if bare minimum is countable. I just don't think the position with value of star after. So yeah. And likewise, all of these numbers share the same property that star n plus star n is 0. You can prove that quite easily. If I have a second king branch, well, clearly the best strategy is to copy your opponent's move. Well, yeah, you do that. Say your opponent chops the top stuff, top, stuff. You then cut the other. Leaving you in a balanced position with your opponent, right? Optimally, you cut the bottom one. It still works. You straight it. You steal.
As long as you guys are both doing the same thing. But
Exactly.
Yeah.
That would show star n plus star n is 0. So all these new star numbers are their own additive inverses, which is kind of interesting. And in fact, these star numbers will in fact form a infinite field order too. I'm not going to say much else about that because it's not exactly what. So now we have these star numbers. We have pink branches, we have blue and green branches, we have the properties of our numbers. Let's go a bit further, shall we? We can start mixing colors, huh? Well, yeah. So, things get more interesting. I'm going to draw a pretty flower. Here's what a pretty flower. Oh, you're welcome. It's just my best piece of artwork so far, ever. So, we have this pretty flower, right? We want to figure out what it's about. Well, let's just play the game and see what happens. Well, let's see. I think the exact analysis for this. Let's see if we can figure
Logan, is it possible for you to use maybe the purple color to see for your pink colors? It's not showing up.
Could you try also the darker green for the
Yeah, use darker green.
The darker green.
This is actually. Yes, no, thank you for letting me know.
Instead of using the regular green.
Yes, I will do that. Thank you for letting me know.
Yeah. No, thank you. So you didn't want to use it. Yeah, that kind of shows up.
Having to, okay,
Yeah, that's way better. Way better. Thank you.
yes, I had to mention, because I'm used to doing this with green as the,
The new color.
yeah. Exactly. You don't get it. Okay, so if you want to play this position, well, let's see. If blue goes first, they can do this to 0 position by chopping the branch, which means red going to lose, but green going to lose. Again, I'm used to the parlance of our thing. So let's see, blue goes first, they're guaranteed. If green goes first, well, they either cut this, leaving blue with the positional value star, or they cut this branch, leaving blue with the positional value of, well, this new weird thing, which is going to be whatever the value of the position where we have a new stock and a blue mark.
Put it down.
Thank you. Whatever the value of this position is. Okay, so if blue goes first, they can win. Red goes first, they can reduce this thing. Well, From blue, blue's best move is to cut the entire stock off, and red only moves to cut the entire stock off. So blue still wins. No matter what. So whatever this value is, it's positive. Well, how positive is it? Can it beat a negative one? Well, so we have y minus one. Okay, so we play this position, and if red goes first, they're not going to come this because that would mean blue would win immediately, as we previously analyzed. So they're going to, well, essentially leave themselves with, yeah, they're going to cut this entire stock off, leaving with star minus one. That's blue to play. So blue is going to cut this, red is going to cut that, and red green. So red, the green goes first, negative. If blue goes first, well, their only good move is to cut this blue range, leaving their opponent with star plus star minus one, which is negative. That's not really a good move. But their other moves are kind of worse. So whatever this thing is, minus one is negative. Let's say it's less than minus one. And less than a half. You're probably used to this now. Less than a four. Less than an 8. Less than 1 over 16. I'm not going to pull the analogies off. It's potentially. So it's also less than all the dyadic fractions. It's strictly bigger than 0. And we can prove it's not equal to star by playing it against star and see. Thank you. So we play this against the position's value.
Oh, purple.
Function populate.
Yeah.
Okay, so we have thing is plus star. Okay, so let's see. Blue goes first. They're gonna go cut this branch, leaving their opponent at 0 position. Red goes first. They're going to also cut this branch, leaving their opponent at 0. I am 99% certain whatever this is, it cannot be a star. I just forget the actual proof. I'm fairly certain this thing plus star. Well, we know that it can be reduced to a 0 position with a single proof. What is that? I plus. I couldn't go so far as to write out the actual position. I don't know if it matters necessarily in the long run. Exactly this thing that equals a star. I mean, do you guys believe me on that?
If you present the proof next talk, I'll take it under consideration.
Well, this is essentially the proof is play out this game.
Mhm.
This thing plus star. It needs to be less, it needs to be a win for the, actually this needs to be less than 0 because then this thing is less than star. Or likewise greater than star. This needs to not be a 0 game.
So is this equivalent to if the purple branch that's attached, where there's 2 things coming off of it, that node, you just move that purple branch away and create a new node, it's equivalent.
Yes, oh, wait, yes, actually, that's how the proof goes. So we're left with this weird thing plus star plus star.
Right, exactly. So then
Which is just this weird thing. So this entire position is also positive. So y plus star is also positive. So y is larger than star. Or larger than the negative star, which is star. So thank you, Ken. So yeah, this thing can't be equal to star because it's larger than. We're gonna give it a funny name. We're gonna call it up. And likewise, there's down. You just flip all the colors.
Or sideways.
Unfortunately, no.
Really stretching our creativity.
I know, Conway Burl Camping Guy, we're not that creative. So,
Certainly not with names.
yeah.
Pretty creative. Pretty creative.
Fun ones if we ever get to.
The down equal to negative up.
Exactly, yeah.
Oh, great,
Down is equal to negative up.
great.
That'll be, yeah, down is equal to negative up. If you flip the colors in a position, you invert the sign.
Two up equal basket.
Two up.
I didn't know you guys were experts on combinatorial game theory.
Also, guess what we call up plus up? Double up.
Couple up.
You have a triple up too.
What if you have 7 up?
Then you have seven. There's actually a position in the book, I'm not gonna write out whose value is 7 up, and it's like five.
Of course, yeah.
Yeah, so now we have up, we have down, we have star. We also can have multiples of up, if we were to say slap 2 of these together, you get, well, 2 up. Which, I don't remember if that's distinct from double up or not. I know double up is larger than up, but still smaller than star. But if the position is value is double up, you don't believe me, you can play it, see what happens. That's the fun part of all the boots or games, you can just literally play them. It looks like a table. Back at the wrong table. This is value double. Like that. Where we show together.
What are the basic questions, triple up?
Yeah.
3 lines total?
I can imagine that getting pretty annoying pretty fast.
Yeah, that's why after 4, you just write it as, like that. So then the triple up is just, yeah. Which is what, yes, so there is the one. So now we're getting very weird stuff. And some things that don't quite make sense. So now, just not the form, the stuff with the stars, the stuff with the stars, so they perfect sense to me. I don't know about you guys. So we, instead of defining, we have some weird numbers showing up. We have some weird numbers showing up. So, and we didn't really know what to do with them beforehand. We kind of had to define them into this. So what if we pull a sneaky and instead of defining our numbers in terms of position, define our positions in terms of numbers. So the following notation will be useful. Define a game G to be the set of all the moves less tens and the set of all the moves right tens in a split. So clearly, if we shove the empty set, well, we define this to be 0. The game with no moves.
The set of all the moves in the first, like at the beginning, that left hand.
Yes, at the beginning of the position. Well, and all the moves they can move to given. It's essentially all the moves they can move to from the initial position.
Given the other person makes a certain move, and then you define what we can.
Yes. So one, we can define as the position where left can go to 0 and right can do nothing. That's the branch where we have one blue branch. Likewise, -1 is the exact split the entire thing, so you split the ordering of these. So 2 is interesting. Because remember, we had 2 blue branches stacked on top of each other. So blue can either go to 0 or they can go to 1. we can either define it like this, or alternatively, because, well, essentially, we ignore the zero, because it's gonna get very cumbersome otherwise, at least with natural. But these are both equivalent to how we define them. And the negatives are you get a negative n and n. So you flip the entire ordering of these and respond. So if G is a game, then negative G is n. So you flip literally everything. I hope the fact that we're using diagonally. I only realized that. So we have this new notation, and it's quite powerful because we can show anything we want on both sides of these. Like any set of numbers or numbers you can come up with, you can shove into these steps. Like, for instance, what do you think the notation for star is? There you go. Well, some players only move is to go to the zero. We show zero on both sides of the bracket. And, well, star 2. Let's see, one player can go to 0, one player can go to star, one player can go to 0, one player can go to star. And you would keep going, writing out all the sets of all these numbers with less than this one on both sides of the bracket for their star. The representation is powerful and it's flexible enough to handle it, which is good, because things are going to get a bit weirder at some point. Like when I mentioned we can shove any set on either side of this bracket, I literally meant it. Because you remember this flower position, right? Well, let's see what it will look like in a notation. So going back to before, let's see. Blue can go to, let's look at the game. Blue can go to this, blue can go to star, blue can go to this weird thing. So, star, blue can go to this weird thing, we still have a value. But we can recursively analyze. You know, that weird thing. Well, blue can go to the 0 position and blue can go to star. And then red can go, green can go to the 0. And then for the actual flower thing itself, well, let's see. Red can go to star, and they can also go to that weird bracket. So this is our notation for top. Everything is moving along.
We match the sort of the or
Right.
that's supposed to be or
I have to double check the actual notation again. I do know there's a simpler way of writing it in terms of this is a simpler way of writing it, but I don't think there's a Hackenbush solution with this actual notational value. Okay.
If if they're balanced, then the actual game is balanced, right?
No. That shouldn't be. Because this notation might look balanced, but remember, up is a wing for blue. Not the top. Which is why I think I wrote this wrong.
yeah, it seems like from the convention before where we have 0 equals empty on both sides. It means if I have the same set on both sides. Like I have the exact same move, right? Well, I guess if certain moves are biased towards one person, because one means one person movement minus one means 3 moves,
Correct.
then yeah.
Which is why I'm thinking I'm making a mistake on the top on the fly.
Wait, so you're saying you can have both sides look the same and still can still not?
Yes, because the one is win for blue, but one on green side is still win.
Oh, right.
If I wrote this out as quickly as I did without making a mistake. This is a simpler notation for pop. Like I said, I don't think tradition with this notation exists in the Hackenbush case. At least I couldn't find it, and multiple other people have been able to find either. But notationally, this is a simpler way of saying it. You see what the foot says inside of that. That's just a bit annoying. Notation can do a lot of things, up to and including, oh, that's all right. So we have up, we have down, we have multiple, we have star, multiple star. Well, if we shove literally any set on either side of it, what's to stop us from, say, shoving the natural numbers on one side of it? You know? We haven't really got there. That refers to an infinite number. I actually would know what one half was. And that's slightly opposite. 1/2 in our new notation. Is, well, let's see. Red goes to, green goes to 1, and blue says blue just go to 0. Now, this may look like I'm taking the average of these two things, but that is not the case. It is unfortunate that this notation looks like that, but that is not what I'm doing at all. That's what 1/2 would look like. 1/4 is kind of similar. You guys write out all the options of both players and reduce what's top. Right. Now we have green county. So what happens if we move away from the finite branch? We kind of have finite blue, green, purple, Hackenbush, gold configuration, in the sense that give me a position with those three colors with a finite number of branches, and you can just use application to analyze it, and you can determine two things from that. It's annoying and can be a little bit more complicated than usual, but it's doable. So what happens if we now throw infinite branches? This is the next logical step. We have finite branches, so now we have infinite. And it's logical, right? And again, this is not
Version Russell. Someone would consider anything having to do with gas.
fair enough.
Right, I think so. Yeah.
Exactly. So we were going to start just stacking infinite number of branches on top of each other. And, well, using our notation, we can analyze this position. It is a position where, let's see, we're, I think it's not doing curly braces and extension brackets. So we're going to 0 for 1, 2, or n, or n plus 1, or etc. And green has no moves whatsoever. So this position is just basically how many moves does blue want to beat himself after he makes a move. You go up a Google number of places, they cut at that branch, you have a Google number of moves left. You still win, but you get a bigger number. Likewise, we can do the same thing with a bunch of red branches. And this is, well, you know the cardinality of the natural number, right? Cardinal, you want to call it omega? We call the value of this J omega. But here's something interesting. Once we allow infinite branches, we don't just get omega. We get negative using the following colors. We get a, well, if we have a single,
So we found a context for the
Well, it's still the zero game because you mirror your opponent's strategy. So what I was gonna get at is you take a single green branch. And you just slap an infinite sequence of blue branches on top of it. Anyone take a guess what this is about? There is no wrong guess. I remember my analysis correctly. Well, let's see, the position. We can go to any of the positive dyadic fractions. Okay, that's the one. And red can go to zero.
There's no red, it's green.
Green, sorry. Again, sorry, I'm too used to it being red. I apologize. We call the position 1 over omega.
Wait, so can I just clarify something for me? So if I cut the bottom blue line segment on the left, yeah, would that remove the rest, all of?
That removes everything above.
Yeah.
Because they're no longer connected to the ground.
Okay, so that still works, okay.
Yes, that's still there. So this position has the value of, well, 1 over omega, also known as epsilon.
Also known as epsilon.
Yeah, it's a small number. You can call it epsilon. It's 1 over this infinite thing. So we can go a little bit, just a little bit further. No, epsilon is not star. Yes, that is correct. Epsilon is not star. Because star is a new number, and there are no pink branches in the picture. So it can't be star. But when you get a little bit further, well, think of any expression where you can shove a real number in. You can shove omega. So I don't have a position memorized on top of my head, but there is a Hackenbush position. There over omega squared makes sense. 2 over omega. Omega over 2. Let's see. The omega root of omega. 1 over that quantity. Then that's the entire thing squared too, if you want to do that. Omega minus 1 also makes sense. Omega plus 1. Omega minus a Google is a valid position.
So unlike every other context in which we work with infinity, here you can operate with it in a meaningful way.
Exactly. Plus, we don't just get omega. We get every other real number as a valid Hackenbush. So pi, e, 1/3 shows up. Actually, 1/5. Negative tangent of pi over 8. Literally any single real number shows up as a valid position.
It's just that you just have different nodes and you can just kind of find a Cauchy sequence, like the rational numbers that represent that real number, and you just
Yes.
have infinite branches.
You find a sequence of kinetic fractions approaching from both above and below. And then yes, exactly. Once you have that sequence approaching from above and below, you can interweave them to get a Hackenbush position with an infinite number of branches that can go to any real numbers or infinite quantities. Now, since we have infinite branches and we have this weird infinity thing that sort of works, I'm going to play one last trick. I don't want to call it a trick, but it's not real.
Logan, I have a sort of a question.
Sure.
Is there a ordered field which contains all these numbers? A concrete like ordered field, like I don't know.
Okay.
Well, certainly not with all of our operations, because we would have contradicted what we were ordering earlier with the previous.
Right.
So I like that you asked that. So given this game notation, I didn't impose any restrictions on it. So 0, 0 is a valid game. However, if we impose a single restriction to our game, on just a game, such that this whole And every single member of the left set is less than or equal to a member of the right set. Then we get the following isomorphism. I'm going to use, can't really use script G. I'm going to make it. Okay, that. Oh, I'll use that. G prime would be the, I don't say set of all games, but it's set of all games in a condition. A isomorphism set of surreal numbers, the class of surreal numbers. As in, the set of all games contains, the class of all games contains the surreal numbers as itself.
We define surreal numbers.
Okay, using this notation with this convention and some addition and multiplication rules that I do not want to, I wrote out the addition rules and I will show you.
So, okay, so then essentially the game of Hackenbush defines surreal numbers. It's a representation.
I can write out the addition rules.
But it's isomorphic to these things that you're writing.
Yes.
Well, I mean, half of these.
With the convention,
By
that every
definition, yeah.
member of the left set is less, actually it's exactly less than if you don't know zero the balance.
What's the equivalent way of constructing the serial numbers?
Yeah,
that we
it's-
have?
yeah. Maybe another way of constructing surreal numbers.
Instead of just being a definition.
Yeah.
So you construct them via this notation. So you start with the empty. You start with the empty thing. And then you define the two. And then you say, well, one is going to be equal to this thing. Negative one is the inverse of that. Then you move forward another step, and two is equal on that day. Then you also get 2, -2, 1/2, and -1/2. Then you get 3 and things like that. And once you have an infinite number of numbers born, you get all the other stuff like omega, e, I, stuff like that. The surreals are something I wanted to touch on, but I want to go in depth into because I'm going to write out the addition rule for it, and you're going to probably hate it. Right. Where x is and so what this means is you take all the members of the left set, add it to y, and then do the same thing in the reverse, and then do the same thing for that set. And that is the separate possible addition rule on the surreal number. I'm not writing out the multiplication one because I didn't write that down. Also wasn't planning on writing this down either. But you can check if this makes sense and it does actually work. I'm not going to bother with that. But ignoring these surreal numbers for 40 seconds. One last thing I kind of want to get to. So you know I mentioned we have for branches a little bit ago. The next logical step after allowing an infinite number of branches is to allow an infinite number of branches all connected to the same branch. And I don't, I should specify, by infinite, I do in fact mean uncountably, or just whatever infinity you want. We have another pretty flower. Well, less pretty than the other one, right? It's slightly more annoying to pin down what this thing is. We can try. Call this thing a value of, I don't know, capital F for flower. Okay, the next thing I'm gonna write out may seem utterly insane. Position wise. So we're gonna take this, we're gonna make a single range. Append this an infinite number of blue branches. Then stack an infinite number of blue, then stack another stack of infinite number of blue branches on top of that. And then again. And we're gonna keep going. We're gonna have an infinite number of infinite stacks of blue branches all on top of this range. Okay. Sorry, I wrote this down in my notes as red. I apologize. So this thing.
Just a master of gaslighting.
I'm gaslighting myself.
Whether it's red on the board and it's reflecting green, all right.
After all, quantum color is the quantum stuff.
He's exploiting the ambiguity of Coilio.
Okay, so this thing has a value of, I'd say drum roll speed. Maybe that's one, the power of omega. So,
Really.
exactly. It is really small. It's very small. I'm going to show you F plus this thing plus in here. So, let's see. Red goes first. Red has one of these infinite number of three branches. There's still an infinite number of those left. Blue goes next. We're going to take one somewhere in this infinite sequence, an infinite number of infinite branches. We're just going to take a finite distance off and chop.
It really doesn't matter.
Exactly. Now, here's the thing I forgot to realize when I was proving this to make it a little bit harder. Every single infinite number of infinite branches of infinite length above them dies when they make that cut, leaving them with a finite number of branches left. So after one cut, this thing is now no longer epsilon to the omega. It's, well, it might not even be epsilon anymore. It's cut somewhere in the first infinite sequence. But it's going to be epsilon to some finite power plus some large natural number. So, Blue's first move, their best move is to go to epsilon to the power k plus some large natural number. His best move is to literally do nothing, keep the position exactly the same. So now red's gonna keep looping back to this position. Blue's gonna keep dropping this n down until the left is epsilon and k. Then they're gonna have to make another choice, whether to cut f or cut another power of epsilon. Logically, they choose to cut the epsilon off because they want to keep the game as positive as possible. So their best move again is to go to something like f minus epsilon to the some number less k. Plus some other large natural number. And, well, you can see where this goes, doesn't it? We can't have an infinite sequence of decreasing orbitals because we started from, we made a cut in finite. We have a finite number of powers left. So essentially, what this is going to boil down to is Blue is essentially, against their will, going to reach the position f minus 1. And, well, we already showed that f is less than all possible fractions. So f minus 1 is less than 0. Therefore, the initial position was also less than 0 because every single possible sequence of moves that Blue and Red make leads to a position.
Okay, so do you want to pick up here next time?
Yes.
Because we're already going to summarize. Yeah, there's going to be a part 2, so be there or be not.